All right. Good afternoon, everyone. Welcome back to ECE 590 seminar. Presenting today is Wentao Jiang. Wentao received his bachelor's degree in electrical engineering from the University of Illinois at Urbana-Champaign in 2019. He's currently a second-year master's student working with Professor Andrew Stillwell. His research area focuses on isolated multi-level converters. All right. Take it away, Wentao.
Can you hear me?
Yep, sounds good.
Okay. So my name is Wentao Jiang, and I'm a second-year master student working with Professor Andrew Stillwell. And today I will be talking about my research project, which is a DC to DC converter. It combines two converter topologies, which are DAB and 4-level FCML. So firstly, I will be talking about the motivation for this project. And after that, I will be talking about the operation of DAB converter and FCML converters. And after that, I will be talking about how I combine these two topologies together. I will also be showing the simulation results and hardware results. And finally, I will conclude by talking about the ambition for this project. So our project is motivated by the energy consumption in the data centers. So our data centers today are consuming a very large portion of the world's electricity. And most of the data centers today are using a AC type power structure. And they are using a topology that is similar to the upper one. And now in recent years, there's a growing number of DC data centers, and they are using a power structure that is similar to the one in the bottom. So the main difference between these two is that in the building level power distribution. So in AC data centers, after they convert the AC grid power to DC to charge the batteries in the UPS, they have to convert it back to AC to power the building level AC power distribution unit. While in the DC data center, after they charge the batteries in the UPS, they do not have to convert it back to AC. So since there are fewer times of power conversion in DC data centers, there will be a lower loss in the conversion in a DC data centers, so that the efficiency can be higher. And since there are fewer components, the size will also be smaller, and it will be more reliable. However, since DC data centers is a relatively recent development, there is a lack of power supplies standards and regulations for the DC data centers. And our project is a high step-down ratio DC to DC converter. And one example application is to convert from high voltage building level UPS, which is around 400 volt to lower voltage servers. And there are several challenges associated with this kind of converter. So firstly, you need to be able to provide isolation between the input and output. So in data centers, the UPS and the servers can have a different ground potential. And if they share a common power line, they can create a ground loop, so that we need to use a transformer to isolate the load from the source. And secondly, in our application, the conversion ratio is high, which is from 400 volt to 48 volt. This can place a large voltage stress across the switches and the transformers. And lastly, we want the power supply to be able to handle a varying load, such as a server, which can consume different power at a different time. So we have finished talking about the motivation for this project. Now I will be talking about the operation of a DAB converter. So a DAB converter is a DC to DC converter, and its circuit is shown below. It has a 4-bridge on the input side and another 4-bridge on the output side. And in the middle, there is a auxiliary inductor and also a transformer. The transformer is used to provide a voltage conversion and also the isolation between the output and input side. The key feature of this kind of converter is that we can use the phase shifter to easily control the power flow in the converter. Now we look at the operation of a DAB converter. So the waveform on the left is showing the steady state operation of a DAB converter. And the phase shift that we want to control is this D value, which indicates the phase shift between the voltage waveform VP and the voltage waveform VS. So VP is the voltage across the inductor and the transformer on the primary side, while VS is the voltage across the transformer on the secondary side. So that N times VS is the voltage across the transformer on the primary side. So when the two are equal, then the inductor current will not be changing. If the VP is larger than the N times VS, then inductor current will be increasing. And if smaller, then it will be decreasing. And then the inductor current is mapped to the secondary side. And because of the switching pattern of the secondary side, the output current will either be mostly positive or mostly negative, which depends on the phase shift. And after filtering by the capacitor on the output side, the final output current will be a non-zero DC current. And using the waveform on the left, we are able to derive equations on the right. Basically, what these equations are telling us is that we are able to control the output current magnitude by simply changing the phase shift value D. We can also look at an extreme case. So if the VP and VS are completely out of phase, the inductor current will still be changing. But since the positive and negative portions are the same, the average value will be 0. So that the output current, the DC output current will also be 0. And this is also predicted by the equations on the right. And despite the benefits of the DAB converter, there are several issues associated with this kind of converter. They need to be addressed if it is to be used in our application. So firstly, in our application, the input voltage is very high, which is around 400 volt. Since in a DAB converter, the voltage stress across each switches on the primary side is equal to the magnitude of the input voltage. The voltage stress on the switches can be very high in our application, and we want to decrease it. And secondly, in our application, the conversion ratio required for the transformer is high, which is from 400 volt to 48 volt, which can increase the volume of the transformer. But we want the transformer to be smaller. And lastly, the DAB converter has a limited 0 voltage switching range, particularly at a light load. And then we want to find a way for the DAB to have a 0 voltage switching even at a light load. So we have finished talking about the operation of the DAB converter. Then we will be talking about the operation of the FCML converter and how to use it to solve these issues in the DAB converter. So showing below is a 4-level FCML converter. We can use it to decrease the voltage stress on the switches. We can also use it to decrease the conversion ratio of the transformer, since the voltage at the switching node is now smaller if we use this FCML. And using FCML, we can also increase the switching frequency at the switching node. which means that we can use the smaller inductors. And since the switching node voltage is lower, the inductor current will be higher, which means that it is possible to achieve zero voltage switching even at a light load if we use the XML. Now we will be talking about the operation of a 4-level XML converter. So the diagram on the right shows the circuit of a typical 4-level XML. The switches A and B are complementary, which means that when one is on, the other one will be off. And the capacitors in the middle are called the flying capacitors. If we size them properly, then the voltage across the first capacitor will be 2/3 of the voltage input. And the voltage across the second capacitor will be only 1/3 of the input voltage. If we use a phase shifted PWM control scheme to control switches, and the waveforms are shown on the left, we can achieve a switching frequency to be 3 times higher than the actual switching frequency of the individual switches. We can also make the switching node voltage to be only 1/3 of the input. And the voltage stress across each switch will be only 1/3 of the input also. So we have seen the benefits of using a XML. Now I will talk about how I combine these two together. So the goal is to create the original waveform, VP waveform, but we want the VP to have a higher frequency, and also to have a smaller magnitude, so that the issues of the DAB can be improved. So what I did was to replace each of the half bridges on the primary side with a 4-level XML, which is shown on the bottom. So now we look at the operation of the new topology. So VSW up is the output from the upper XML, while VSW down is the output from the lower XML. Since we want to create the original VP waveform, and VP is the difference between these two outputs, we operate these two XMLs using the same frequency and the same control scheme, but we want them to be operated completely out of phase. And using this kind of control scheme, we are able to generate a VP that is similar to the original, but now it has a frequency that is 3 times higher, and the magnitude is smaller. Since the frequency is higher, we are able to use a smaller inductor. And since the voltage conversion ratio is smaller, we can use a smaller transformer. And because we replace the half bridges with the XMLs, the voltage stress across each switch will also be smaller, which means that it is possible now to use faster switching devices such as gallium nitride. And if we switch the secondary side 3 times faster, we are able to still use the phase shift to control the power flow. And now I will be showing the simulation results. So I did a simulation in the PAX, and the circuit is shown below. I set the input voltage to 400 volt. My target output voltage will be 48 volt. And target output power will be 600 watt. And the switching frequency for the primary side switches will be 200 kilohertz. And so that the secondary side switching frequency will need to be 600 kilohertz. Firstly, let us look at the voltage stress across each switches on the primary side. So I was monitoring the voltage across each switch while running a simulation. So as we can see from the waveforms on the right, we can see that the peak voltage is around 133 volt, which is around 1/3 of the input voltage. This confirms that the voltage stress on the switches have been reduced. by using the XML. Then we look at the voltage output from the individual XMLs. So we are operating the switches with a phase-shifted PWM scheme. And the control signals are the top three waveforms. The bottom one is the output from the individual XMLs. So we can see that the voltage output has a frequency that is 3 times higher than the individual control signal. And the peak-to-peak value, the peak-to-peak voltage magnitude is around 133, which is 1/3 of the Vin. And the reason that it's going from 130 to 260 is that I'm using an overlapped control signal. And the waveform on this page shows that if we operate the two XMLs completely out of phase, we can create a VP that's similar to the original one. But now it has a higher frequency and a lower magnitude. Finally, if we compare the simulation to the original DAB, we can see that the waveforms are similar, except that the voltage is smaller and the frequency is higher. And also the inductor and the output current are similar to the original one. And we want to see if we can control the output power using the phase shift. So we fixed the inductor value to 4.7 microhenry. Then using the output power and output voltage, we can calculate a phase shift, which is 0.22 to achieve the output power. Then using this phase shift in the simulation, we can see that the output voltage after filtering is 48 volt. And the output current is around 12 amps, which means that the output power will be 600 watt. This confirms that the controlling using a phase shift is working. For the hardware, we received the PCB last week, but we have not yet finished assembling it. So there's no result to show yet. And I have included a list of parts on the right. And finally, I will be talking about my ambition for this project. So firstly, I will try to finish building and testing the board. After that, I will try to replace the Han1 transformer with a planar transformer to further reduce the size. And finally, I will try to implement feedback control. So basically, I have a feedback from the output to the microcontroller unit. And I want to use it to automatically control the phase shift to control the, to change the output power. And that's all I have for today. So thank you for listening. Do you have any questions?
Hey, Wentao, can you hear me?
Yes.
Okay, awesome. So first of all, very clean presentation. So thanks for the presentation. It was very clean. I have a couple of questions, Wentao. One is if you go back to one of your slides where you had the topology, I'm curious if there is any where you had the entire topology. I don't remember the slide, sorry, where you had combined the FCML with that of the dual active bridge. You had a topology there. Yeah, this one is fine. I'm curious if there is any advantage of increasing the number of levels on the output side, or is it like it doesn't matter too much?
So there's a trade-off between the size of the capacitors and the size of the inductor, like by changing the levels.
No, I'm saying that on the output side. So like your multi-level right now is all on the input side, right? As I understand. Like, is there any advantage of adding more levels on the output side, or is it not really something interesting?
So if we increase the levels of the XMLs on the opposite, then if we use the XML on the opposite, then I think the voltage stress across each switch will be smaller. But since the original voltage stress is already smaller enough, which is around 48 volt. So I do not think we
got it. Got it. Okay, that makes sense. And the second question I had was, so one of the motivation when you said was to reduce the size of the transformer, right? So I'm curious, like if you guys did any calculation in terms of, so what we are doing here is a trade-off of adding more switches and capacitors and trying to reduce or operate at a higher switching frequency. Is there a calculation where how much is the improvement on the size of the transformer? Is there a straightforward way to answer that, or it is more complicated than what I can think of?
So if the conversion ratio is smaller, if the conversion ratio is too large, then if we use a planar transformer, we will need to like use more levels in the transformer PCBs, which is harder to build.
Sorry, I'm being slow here. So what I'm asking is, imagine you only had 2-level. You didn't have 4-level or this FCML club to the dual active bridge. Imagine you had the size of the transformer. How does it change if we go on increasing with the? Is there an straightforward relationship conceptually? If I can understand, is there a way to think about it? As I go increasing the number of level, I'm curious to know, like, how will the size of the transformer change, or what is it dependent upon?
Oh, okay, I see. So if we increase the levels of the FCMLs, then the voltage at the switching node, which is on the left of the transformer, will be smaller. So if this voltage is smaller, then the conversion ratio required for the transformer will be smaller than the original.
Okay.
So I'll add a quick comment. The main mechanism that adds the improvement is the higher switching frequency. So if the switching frequency on the primary side and the secondary side remains the same between our two scenarios, then there isn't actually much of a benefit at all in terms of the transformer. But if we're now using lower voltage rated switches and we're switching, instead of switching, say 400 volt rated switches, we're now switching, 100 volt or 200 volt rated switches, we should be able to switch those faster. And we have the benefits of the FCML as well. And so fundamentally, it's really just the frequency gain. We don't get a lot of benefit from the other aspects of this. Because our flux is fundamentally still the same, because when you think about our secondary side, that volt second doesn't change.
I see. So Andrew, again, maybe Wentao can answer as well. My point is, like, for an inductor, it is easier for me to think about it that, okay, if I go with a higher switching frequency, I will have a lower ripple. But here, how do I see that for a transformer? That's what I'm it's not clear in my head.
I mean, you're still going to have a smaller BH hysteresis loop. Let's see here. What's the right way of putting this? No, the hysteresis loop is not changing. We're at a higher frequency, which has some benefits. The voltage level is lower, so our tolerances and our spacing is a little bit better. But those are really fundamentally it. The benefits, we state that there are some benefits to the transformer in terms of size, but they are not as dramatic as what we've seen for the inductor and the FCML in the past, for example.
I see. Okay, yeah, because
it's not the n squared or
right.
we've seen in the past. They're at most linear. As opposed to a squared type of situation.
I see. Okay, perfect. Thanks so much, Andrew and Wentao. Again, Wentao, very clean presentation. Thank you.
Thank you.
Are there any more questions? I don't think there's any more questions. So thank you, Wentao. Great presentation. And I guess everybody else have a good afternoon. Thanks.